Okay, so the first of these three probability practice problems is the fat quarters. This is a tough one for me just to wrap my head around the context of it, but then it's also kind of a tricky probability question. So they explain to you how the manufacturing process of these fabrics work, and that they get defects. So X is the number of defects, and then the probability of those number of defects is accompanying it in this table. So if a fat quarter has more than 2 defects, okay, so that means these guys here, it's discarded, all right? So it's not going to be sold. Y is going to represent the number of defects on a fat quarter that can be sold, okay? So if we're talking about fat quarters that can be sold, what becomes my whole entire world or denominator is now, these can't be sold. We want the ones that can be sold. So I have to take this 0.08 and subtract it from 1. And what's left is 0.92. Only this becomes my entire world. So now the probability of 0 is no longer 0.58, but it's 0.58 given that the fabric was sold, right? These are all conditional probabilities. And then I'd have 0.23 divided by 0.92. And I'd also have 0.11 divided by 0.92. That becomes my new probability distribution. So what I want to do is put that in my calculator right away. So I go to Stat and Edit, and that's my new list, right? The fat quarters with 3 defects or 4 defects are not getting sold. So the only possibilities are 0, 1, and 2, and then these probabilities have to add up to 1. So how do I get the mean and standard deviation? The easiest, quickest way to do that is we go to Stat, Calculate, and we do our one variable stats. Now, if your calculator menu doesn't look like mine here, you don't have the list and frequency list. Most of you do. So you'll enter it this way. If you do not, then your calculator is just going to look like this. Some of the older calculators, you'll just write one variable stats, L1, L2. We execute that. And here is my mean, okay? And then my standard deviation, notice they don't give me a sample standard deviation. It's only population because we know this is a valid probability distribution. When it says show your work, what I would do is just look at my formula sheet and see, well, here's the formula for expected value, okay? Here's the formula for standard deviation. Just throw a square root over that. That's for variance. So if we take the square root of that, I would just write that formula down. We don't have to do all of the heavy lifting. We let the calculator do that for us. Otherwise, it would take us a lot longer to do a problem like this, right? Just to get the mean, I'd have to do 0 times 0.58 plus 1 times 0.323 plus 2 times 0.11. Then I'd have to employ the next formula. I'd have to take that mean that I get, 0.489, and over, right? 0.489 minus 0.58 and so on. So, or minus 0 rather, times 0.58. I would just write those, copy those formulas down off your formula sheet, and that should account for the show your work part. Okay, so that was actually part B here, right? Part B is 0.489 and 0.699. I jumped through part A pretty quickly. Part A is what I had in my calculator right here. That's my new probability distribution. Okay, kind of forgot that was part of the question. So that's A and B. Now we come to company G. What's going on here? Company G is a totally different company, and they're telling us, okay, here's the average number of defects. So it's something different. We did up here the number of fat quarters that were going to be sold. These are the defects. And what they're saying is every time company G sells a fat quarter, they sell it for $5. Okay? But they're going to pay $1.50 for each defect. That's their average number of defects. Okay? What are the mean and standard deviation for the selling price? Okay? So the first linear transformation for mean should be kind of intuitive, right? The mean it's going to be $5 each, but they're going to lose $1.50 for each defect. And the probability that they get defect is 0.4. Just a linear transformation. Now, what do we do with the 0.66? Well, remember, standard deviation is not affected by adding a constant. So this 5 is not going to affect the standard deviation. Neither is this negative sign, right? It's always positive. So I'm just going to take, for the standard deviation, I'm going to take 0.66 and just multiply it by $1.50. And that'll give me my standard deviation. Okay, this question I think was actually on an AP exam many years ago. It sounds very familiar to me. But I have 4 runners. And again, you want to make sure you read the narrative up here so that you're familiar with the context of this, right? They're planning to participate in a race in which each runner runs a mile. The team time is the sum of individual times. Okay, that's key for the 4 runners. Assume that the individual times for the 4 runners are all independent. That's helpful. And the individual times for these races are approximately normally distributed. We want to lock in on that. As soon as I start seeing something like something's normally distributed, I want to start thinking about this, normal CDF, right away. And we all know these are pretty easy problems, right? The normal CDF. So let's look at part A, see if it's an easy one that we can just steal here. Runner 3. He thinks he can run a mile in less than 4.2 minutes. Well, let's check out runner 3. Runner 3, his time is normally distributed, and 4.5 lives in the middle of that. That's his average time. Well, he thinks he can run it in under 4.2. He thinks he can do that, okay? So we would just take normal CDF from, let's say, -10. I think 0 would actually work. That's our lower limit. Then we have our upper limit, which would be 4.2. Our mean is 4.5, and our standard deviation is 0.14. So hopefully that was an easy one on this. You steal at least 1 point on this open-ended, then get some partial points, and at least get a 2 on a question like this. Okay, so now for part B, the distribution of possible team time. So let's remember what the team time is, right? The team time is the sum of individual times. So for part B, the mean is going to be real easy. The mean team time is just going to be the sum of all their times on average. 4.9 plus 4.7 plus 4.5 plus 4.8. Jeepers creepers. That's supposed to be a 4.8. Okay, so I just add them all up. Now for their standard deviation of their team times. Okay, they give me all the individual standard deviations. Okay, say it out loud with me together if you remember it. I think some of you are sitting there and you know what rule is coming here. I can't add the standard deviations. Okay, but what can I add? We can add the variances. Variances always add. Doesn't matter what we're doing with the variables. So I take 0.15 squared. That's a variance. I take 0.16 squared. That's a variance. I take 0.14 squared. That's a variance. And then I take 0.15 squared. That's a variance. I don't want the variance. I want standard deviation. So take the square root of that. Standard deviation is the square root of your variance. Okay, so that's part C. Okay, and then finally, suppose the team's best time is 18.4 minutes. What is the probability the team will beat its own best time in the next race? So that's another normal CF. I didn't do the calculation there. Okay, but whatever you got for their, goodness gracious, whatever you got for their mean in the previous part, tuck that in the middle. Right, and then you're going to normal CDF that with the mean and standard deviation that we got in part B. That's how this one works. So this one was heavy computational. Hopefully you remember that variances always add, and this is a very gettable 4-pointer for many of you. Okay, so another reason I picked these 3 problems is they were heavy on computation, which for me feels like they're very gettable, rather than sometimes it can be hard to explain yourself. It can be hard to find the right words to explain. Here's why we would use a stratified design, or here's why we would use a block design in an experiment. Why do we have this control factor? Sometimes it can be hard to articulate ourselves to someone and explain it clearly, and then we get judged on that. Whereas here, if we get the right number and we can show our work, nobody can criticize us for that. Okay? But the trade-off is a couple of these questions are a little tricky, right? So the probability that there's a coach class ticket holder who flies frequently will upgrade it is 0.1. What's the probability that Sam's first upgrade, I don't know if you remember this, will occur after the third flight? This is a geometric setting, but I don't even like to say, oh, it's geometric. I like to approach this from just a basic probability standpoint, okay? What this means is, what's the probability this first upgrade will occur after the third flight? So that means it's going to occur on the 4th, or the 5th, or and so on. Anything after any of those, 4th or 5th or 6th. So it's an infinite geometric sequence for all my calculus friends out there. So the probability that it occurs after the third flight, what I'm going to do is find the probability that it occurs on the 1st, or on the 2nd, or on the 3rd, and then I'll subtract that from 1. Okay? So the probability it occurs on the 1st is just 0.1. Now the probability it occurs on the 2nd means that it did not occur on the 1st, that's 0.9, and then it did occur on the 2nd. Okay, probability that it occurred on the 1st, or it occurred on the 2nd, or let's have it occur on the 3rd. That means what happened? It didn't occur on the 1st or the 2nd, so I take 0.9 squared times 0.1. Okay, this is the probability it occurred on the 1st, or on the 2nd, or on the 3rd. Subtract that from 1. And what we have is the infinite geometric sequence of 4 or 5 or 6 and so on. Okay, add all those up. So that's a little tricky, but it's gettable. It's like the birthday problem, which is how I introduced probability to you all. What is the probability that Sam will be upgraded exactly 2 times in his next 20 flights? This is a binomial setting. That's why I wanted to put this on here for you. There's going to be 20 trials. It's a classic binomial setting, binomial PDF. We're not adding a bunch of stuff up. It's just one particular instance. We're going to look at 20 trials. He's going to go on 20 flights. The probability he's upgraded is 10%, and we want him to get upgraded exactly twice. So if you remember that binomial setting, you don't need to use your formula sheet. You can just use the calculator. Okay. Now, he's going to take 104 flights next year. Would you be surprised if Sam receives more than 20 upgrades to first class during the year? So there's a couple of ways we could do this. I think if you're calculator savvy, we just go with binomial CDF. They may find the mean and standard deviation of this, right? You take 104 times 0.1. That would be your mean. Okay, and then to get the standard deviation, we take 104. I think this is the harder way. I don't think most of you need to go look up these formulas. 104 times 0.1 times 0.9. That's my standard deviation. And then I just do normal CDF, right? So I put this number in the middle of my normal curve, and then more than 20, and then I just shade to the right of 20. I think this is easier with a binomial CDF, especially since you have the calculator that would do it. All right, if you have a calculator like mine, okay, that always adds up for CDF 0 to a number, okay? We want to know that the probability that Sam receives more than 20 upgrades. So what my calculator can do, the way it's configured with binomial CDF, he's going to take 104 flights. The probability that he's upgraded is 0.1. My calculator will add up the probability that he gets anywhere from no upgrades to 20 upgrades. Well, that's not what they want. They want more than 20 times. So subtract that from 1. If you have an Nspire, I think you can just put in 20 as your low limit. 21, right? So if you were doing this on your Nspire, and I'm struggling with my touchscreen, so I'm just going to go right into it. It's binomial CDF again. But on the Nspire, you still put in your 104 trials. You put in 0.1, but then you would put in more than 20, so 21 to 104. Have the calculator add that up for you. So 104. Have the calculator add that up for you, and you'll get it that way. Okay. So hopefully this is some good review of probability. We still have time to keep working on these. If you haven't noticed, I'm trying to lock in on one of the different units or topics. The way College Board breaks up the course is a little different than how I do, but I kind of break it up by the textbook chapters in our book, but sometimes I'll lump them together and talk about like chapters 1 and 2 together. Chapter 3 is regression, correlation, that kind of stuff. Chapter 4 is its own thing, experimental design. They have units, so the AP exam is going to cover units 1 through 7. So for us, that's chapters 1 through 10 of our textbook. Next week, when we dive into these, the next ones coming will probably be, maybe we'll have some more binomial stuff, but some central limit theorem, some statistical inference is probably the direction we need to head in next, which is mostly familiar to you. But you'll see, I'll double back to one variable statistics, linear regression, correlation, experimental design. We'll try to hit on all of those, so we're nice and prepared for the exam day.